Hey everyone, this is Introduction to Computing and Programming in Python and Multimedia Approach, the 4th edition, Chapter 7, Modifying Sounds Using Loops. So the chapter objectives for Chapter 7 are to understand how do we digitalize sound and the limitations of human hearing that allow us to digitalize sounds, to use the Nyquist theorem to determine the sampling rate necessary for digitalizing a desired sound, to manipulate volume, to create and avoid clipping. The computer science goals are to use arrays and data structures, to use the formula that n bits results in 2 to the n possible parameters in order to figure out the number of bits needed to save values, to use the sound object to debug sound programs, to use iteration as such as for loops for manipulating sound, to use scope to understand when a variable is available for us. So digitalizing sound. How do we get that into numbers? Remember that in calculus, estimating the curve by creating angles? We do the same thing to estimate the sound curve. Analog to digital conversion will give us the amplitude at an instant as a number, a sample. How many samples do we need? Sounds as arrays. Samples are just stored one right after the other in the computer's memory, like pixels in a picture. That's called an array, and it's an especially efficient, quickly accessed memory structure. So we can see in the bottom of this illustration, there's 5 indices, right? Index 1 holds 59, index 2, index 1 and index 2 hold 39, index 3 holds 16, index 4 10, and index 5 is -1. So working with sounds. We'll use the pick a file and the make sound functions built into JES. We want wave files. We'll use get samples to get all the sample objects out of a sound. We can also get the value at any index with get sample value at. Sounds also know their length, get length, and their sampling rate, get sampling rate. And we can also save sounds with write sound to, which takes 2 parameters, sound, and then the file path. So we can demonstrate working with sounds in JES. So at first what we do is create a variable called pick a file. Then we can print that file out and see what it looks like. Then we say sound equals make sound, and we convert that to a sound. Then we can actually print the sound, and it shows us the length, the sound length. We can say get samples, and we can print sample values at different things, and then we can actually explore the sound. So let's go to JES real quick. And let's do sound equals make sound, pick a file. So let's just get a file to start with. So we're going to go to desktop, wherever you guys have your file locally. So I have week 1 and I have lope sound. So now I have something in my sound. So I have sound file, it points to where it is, number of samples, 53,040. So now we're going to continue and we're going to say samples equal get samples of the sound. So we're going to say samples equal get samples. And we pass in the sound object. So now we can print samples. It's taking a second to load. And then we can see once that's done. Let's see, still loading. Let's go back to here for a second. It's taking quite a while for this to actually load. So samples is probably a pretty big array, especially based on the size of the wave file that you actually have. So it could actually make JES run pretty slow depending on how the file size. Um, so definitely go ahead and test this out. Make sure you don't get stuck. If it does get stuck, like in my example, make sure you know how to close JES. Um, we can just do this real quick. We're actually going to end up closing it like this. Okay, let's reopen another JES instance. And what we'll do is we'll do the exact same thing again. Again, I'm showing you these problems. I'm running these problems on purpose. Uh, Not so much as planned, but it helps you guys be able to troubleshoot what's actually happening with your guys' files. Oops, with your guys' programming as well. So if you guys have this similar problem, you'll see, oh, Professor Carpenter had the same issue when he was going through, so it's a common issue, right? We all make mistakes, and we're not, no one's perfect with our programming, so it's okay to make mistakes for sure. All right, so again, we're back to where we were with printing the sound file. And then let's do what we're going to call get sample value at. So we're going to say I'm going to say print get sample value at. I'm going to pass in sound. I'm going to say 1. Awesome. Let's say 2. Let's say 3. And so on and so forth. So we can see that we're accessing the array of samples that is returned, and then we can actually get the index from that samples array. Actually, let's do one more thing. We're going to do explore sound too. So we'll do explore sound. Cool. So we can say play entire sound. I don't know if you guys can actually hear it in this video, but it's actually playing this antelope sound. And we can actually go to see where it says current index. So I can go to 1, and we see at index 1, it's negative 56, which is just what we printed here, get sample value at, right? We can say index 2, negative 4, also what we got. 3 should be 37, so on and so forth. And we can actually see it moving here as well, right? Cool. So I can say play entire sound again, and again it plays it. We can zoom out, we can zoom in. So definitely mess with the Explore feature that's built into JES. It's nice to get to be able to see the sound and go through and see the actual sample values at each indice as well. So demonstrating working with samples. So we can print the get length of sound. Let's try that. So we can do get length. Let me print the sound. Awesome. 53,000, 40. We can do get sampling rate. Print get sampling rate of sound. 22,050. Awesome. Same as that one. We can also do get sample value at that. We already did that. But what happens if we do get sampling value at? So let's try another example. And let's say we do, cool. So we got an error, right? You're trying to access the sample at index 66,666, but the last in this index is at 53,039, right? So there's an error that you guys might see. That's basically saying you're trying to access an index that doesn't exist, right? I only have 53,000 samples, and you're trying to access one at 66,000, which just does not exist. Cool. So working with samples, we can get sample objects out of a sound with using get samples or get sample object at. A sample object remembers its sound, so you can change the sound or the sample object, the sound gets changed. Sample objects understand get sample and set sample. So here's an example of changing samples. Again, we get the sound value. We can print a sample. So I can say get sample object at. Let's try this. So I can say get sample object at fixed sound 1. Cool. Sample at 1 with value negative 56. And then we can go through that, and we can get samples and set samples as well. But there are thousands of these samples. How do we do something to these samples to manipulate them when there are thousands of them per second? We use a loop and get the computer to iterate in order to do something, right? Computer programmers and software engineers and so on and so forth, they're lazy, right? We don't want to repeat stuff. That's why we have programming. We can make it do the hard work for us, so we don't have to waste time setting thousands of samples and wasting thousands of seconds and minutes and whatever it is, right? So here's an example of a loop. We say for sample in get samples, the value equals get sample at sample, and then we say set sample to the value. So here's a recipe to increase the volume. So we define increase volume. It's a function that takes one parameter, which is sound, and we say for sample and get samples. So we're saying for every sample in this list of samples, right? It kind of makes sense. And then we're gonna set the sample value to sample and then value times 2. So let's actually try this out. So we're gonna define a function called increase volume that takes in sound. And then it says for sample in get samples of sound. We're going to say, let's go back to our example again. We're going to say set sample value. And we're going to say sample. And we're going to say get sample value. sample times, I believe it's times 2. Awesome. So let's load this program. We're going to load it. We're going to call it test like normal. Let me clear this command window again. We're going to load it. All right, it loaded fine. All right, so let's see if we still have our sound here in this scope. Awesome, sound's still there. So now we're going to say increase volume. Actually, let's do one thing real quick. Let's explore sound again. So we can look at what so this is what our wave pattern looks like. Now let's see if we can actually say increase volume of sound. Awesome, it did that. Now let's explore it again. So now we can actually compare. Here's our original, and this is our original here, and this is our increased volume, right? We can definitely tell that it spiked these wavelengths. So if I play this, my ears are probably going to get destroyed. All right, so it's definitely louder. I don't know if you guys again can hear that, but it's certainly louder than it was originally. But again, we can tell that because we can see what the wavelengths look like. So we can compare this next to each other, and it's definitely increased the volume. So something as simple as this, right? We're saying for every sample in the sample list, just increase the volume by 2. So how did that work? When we evaluate increased volume, the function increased volume is executed. The sound in variable s becomes known as sound, and sound is a placeholder for the sound objects, s. So starting the loop, get sample returns a sequence of all the sample objects in the sound. The for loop makes sample be the first sample as the block is started. So we can see when we call get samples, the first sample in the for loop is index 1, which is 59. And then that continues, that does everything in the for body, and then it continues to the next index 2, which is the value of 39, and it goes so on and so forth like that. So executing the block, we get the value of the sample named sample. We then set the value of the sample to be the current value, variable value times 2, right? So that's inside the for body. So this is our function scope. Everything inside here is our function. Here's our for loop, and then this is everything inside the for loop. Everything that's indented over underneath the for loop. So we have a colon that denotes that this is a for loop. So anything in here is going to repeat. So anything down inside this indented area of the for loop body is going to repeat for the number of samples that are in sound. Then we have the next sample, and then that continues to go on. Oops, that continues and repeats throughout the entire list of samples. So are we sure that worked? So we can this is what we just did, and we can actually see in their example too, the right side does look larger. So what if we wanted to decrease? We would actually multiply by a percentage or a number less than 1, right? So if we multiply by 1, it's going to be the same thing, right? We all know that. If we multiply by 2, it's going to double it, right? And then if we multiply by 0.5, like in this example, it's half of it. So we can try decreasing if we want to. We know it's actually going to be 0.5. So let's just run this. So I'm going to explore the sound one more time so we can see this up here. Again, it's our increased sound. So now let me increase the sound volume. This is actually a bad name, right? Because we should always make our functions the same name of what they do. Make sure you update that. All right, so that loaded. So instead of calling this increased sound, I'm going to call this decreased sound. That's done. Want to explore that. Awesome. Right? So we see a before and we have an after. Now let's decrease it one more time. Let's explore it again. Even more, even tinier. So we have our original, and we decreased it twice, and we can see that it's definitely changing how the loud that sound is. So can we make it generic? So now this is saying we say change volume and it's sound and a factor, right? So how do you think this works? So what we can actually do, right? Because instead of decreasing and increasing and making two functions, yada yada yada, we just can say like something like this, right? We just multiply this by a factor, and then we can pass in whatever we want. So let's do this, and we're gonna call change. Oops. We're going to call it change volume. And it takes two parameters. The first one's sound, the second one's a factor. Awesome. And then we can see that again, this gets smaller. But what if we want to increase it? Or what if we said let's increase it by 5? We can explore it again, and it's relatively close to what it was originally, right? So this is a way to make your function generic. The more you can make your functions reusable and make them generic, the easier they are to use, the more obviously reusable they are. And it's definitely a best practice to keep your methods in a way that they are pretty generic overall. So here's an example of that, what we just did. Does increasing the volume change the volume setting? No. The physical volume setting indicates an upper bound, the potential loudest sound. Within that potential, sound can be louder or softer. They can fill that space, but might not. Have you ever noticed how commercials are always louder than regular programs? Louder content attracts your attention. It maximizes the potential sound. Maximizing volume. How then do we get maximal volume? Or automatic recording level. It's a three-step process. First, we figure out the loudest sound, which is the largest sample. Next, we figure out how much we have to increase and decrease that sound to fill the available space. We want to find the amplification factor, amp, where amp times loudest equals 32,767. In other words, amp equals 332,767 divided by the loudest. Finally, we amplify each sample by multiplying it by the amp. So maximizing or normalizing the sound. So here's our function for normalizing sound, largest equals 0. We go through and we find the maximum of the largest versus the sample value. And we have amplification equals 32,000 again divided by largest. And then we print it out. So max is a function that takes any number of inputs and always returns the largest, right? So in this example, we can say max of 1, 2, and 3 is 3. Max of 4, 67, 98, negative 1, 2, and 90, negative 1 and 2 is 98. There's also a min function which works similarly but returns the minimum. So, or we can use an if instead of the max, right? Which also works, but max is also just, it's built into Python. It's an easy to use function, so you might as well do that as well. So I definitely recommend taking this as an example. Um, we can here let's actually do this. So we're gonna say get samples of the sound, and we're gonna say the largest equals the max of the largest. Okay. So what we're gonna do is we're gonna say largest equals 0. I'm gonna get rid of this. So it's gonna go through each example, and then we're gonna update with our largest value. Largest equals the max of largest, and we're gonna say get sample value. Get value of sample, and then amplification, amplific, amplification, sure, equals, I believe it was 32,767, 32,767.0 divided by the largest. And then we're just gonna print out, actually, let's just return amplification. Copy and paste. Make sure your variables are always the same spelling, or you're gonna have some weird issues. Actually, let me hit no real quick. So we don't actually care about factor anymore. So let's get rid of that because it's not that. And let's just call this find amp. Actually, no, let's call it get amp. So normally you actually want to name your functions what they do, right? Since we're returning the amplification, get amp makes the most sense for what we're doing. Awesome. So let's call it get amp, and let's say sound. Awesome. So the amplitude here is 1.6, according to what our function said. So let's continue. So that's the amplification factor. So aside from positive and negative extremes assumed to be equal, we're making an assumption here that the maximum positive value is also the maximum negative value. That should be true for the sounds we deal with, but it's not necessary, or it's not yet. It's not necessarily true. Try adding a constant to every sample. That makes it non-cyclic. The compressions and rarefactions in the sound wave are not equal, but it's fairly subtle what's happening to the sound. Why 32,767.0 and not 32,767? Right. So if we look at the example, we remember that there's a difference between the integers and floats and doubles and so on and so forth, right? So if in their first example they print 1.0 divided by 2 and it's zero point 0.5, or 1.0 divided by 2.0 and it's zero point 0.5 again. But what if we just do 1 divided by 2, which is both integers? That just results in 0, right? Because it takes the type of number that we're dividing by originally, and that's how it gets the calculates the output that we want. So this is the way that Python just handles numbers. And if you give it integers, like I said, it only ever compute integers. So avoiding clipping. Why are we being so careful to stay within range? What if we just multiply all the samples by some big number and let them go over 32,767? The result then is clipping. Clipping is the awful buzzing noise whenever the sound volume is beyond the maximum that your sound system can handle. What if we maximize the sound? All samples over 0 make it 32,767. All samples at or below make it negative. So all clipping all the time. So we can say maximize sound, and then we can actually go through each sound value, and then we can say if the value is greater than 0, set it to the highest number, and if it's less than 0, set it to the lowest number. And then we can see that in this example, which you guys can take, it converts this nice looking wave file into something that looks more like a barcode because of how we're setting the sample values instead. We can hear the speech. Try it. You can understand speech in this mangled sound. Why? Implications. Human understanding of speech relies more on frequency than amplitude. Note how many bits we need per sample. A single bit per sample can record legible speech. Processing only part of the sound. What if we wanted to increase or decrease the volume of only part of the sound? How would we do it? We have to use a range function with our for loop. Just like we did manipulate only part of the picture by using range in conjunction with get pixels. So that's an example of what you guys can do with various sound files. We learned quite a bit of how to access the array. It's not too different than how we access pixels with JES. So I definitely recommend going through these examples that we did. Again, it's okay to make mistakes like I did. That's totally acceptable. We're learning this stuff together. And just go ahead again and take these examples. And if you have any questions, as always, feel free to reach out and let me know, and I'll be happy to help. Thanks, guys.